This is Jack Jackson. In this video, we're going to be talking about a 1 proportion z-test and a 1 proportion z-interval. These are approximation techniques for doing tests of proportions for one sample using a normal approximation. So this section shows how to use a normal distribution to approximate a binomial or hypergeometric distribution with computing p-values for hypothesis tests concerning proportions. Although this method really should not be used to compute p-values, it is a standard procedure in entry-level statistics texts. Recall that the probabilities from distributions of proportions should properly be computed using a hypergeometric distribution. However, if the population size is large, we can use a binomial distribution as a good approximation. Furthermore, if the sample size is also large, then we can effectively use a normal distribution to approximate the binomial and hypergeometric distributions, which is what this video is about. So in a binomial distribution, let n be the number of trials or the sample size, lowercase n. X, remember, is the number of successes in a fixed number of trials or the number of successes in the sample. P or P sub 0 or just P is the probability of success on one trial or the proportion of successes in the total population. Q then is 1 minus P, or the probability of a failure on one trial. In other words, the proportion of failures in the total population. And you may remember for binomial distributions that mu is n times P, and sigma is the square root of n times P times Q. So we know the mean and standard deviation of a binomial distribution. A binomial distribution can often be approximated quite well by a normal distribution with the same mean and standard deviation. This approximation is better when the sample size is large, and also the closer P and Q are to each other, and thus to 0.5, the better the approximation is. One rule of thumb is that a normal distribution provides a reasonable approximation of a binomial distribution when both NP and NQ are larger than 30. I've seen some textbooks use a less stringent criteria than that. So some people will allow that with a less stringent criteria. But my experience is we need something like this. In the previous video, we saw some examples worked out where we did side-by-side binomial and normal, looking at what would happen if the p-values were certain combinations there, or even hypergeometric binomial and normal approximations, and see what would happen. And we saw that we could be pretty far off if we don't get a large enough sample size. But we can approximate with a normal distribution pretty well if both NP and NQ are greater than 30. So P is the probability of success on one trial. Again, Q is the probability of a failure on one trial. And then we know the mean and standard deviation of the binomial. And the way we're going to do that is, well, we're going to use a normal distribution with basically the same mean and standard deviation for proportions. Here I'm going to show you real quickly a series of graphs of a binomial PDF with a normal distribution with the same mean and standard deviation. So as we move through these examples, N, NP, and NQ are all getting bigger, so the approximation gets better and better. Here's a binomial with N is only 5. And of course you can see it's quite a bit of difference in the distribution. Whereas if we increase it to 10, it's better. 30, now it's getting to be actually a pretty good distribution. I made P to be 0.4, so it's not perfectly symmetric for the binomial. Of course it always is for the normal distribution. But we're getting pretty close. 40, that's even better. And there's 100. And of course, once it gets up to really big, like 1,000 for our sample size, it's very, very, very close. We can hardly tell them apart. So clearly, we can see that if the sample size gets large enough, a normal distribution is going to be pretty good as an approximation. Now, one thing we should remember is from a binomial distribution is about the number of successes in a sample, X. But when we deal with distribution of proportions, we're dealing with p hat, the proportion of successes in the sample, which might be a percentage or a decimal value. And of course, there's a real easy relationship there, is that p hat is just x divided by n, or x is n times p hat. So when we did a binomial distribution and we got the mean is np and sigma squared of npq, we can just sort of substitute these over here for the mean of a distribution of proportions. Well, since this is a mean for the x values, the mean for the p hats would be n times this, or this would be n times the p hats. So take the mean for the p hats and divide this by n, and we get the mu over here is just p. And then the standard deviation, we take the standard deviation here and divide it by n. Here I rewrote n at the bottom as the square root of n squared, and distribute that, or not distribute, but just do some canceling there. And we get that pq over n is this, and then to the square root is the standard deviation. So if we're going to use a normal distribution to approximate our proportion distribution, this is the mean and standard deviation we want to use. And of course, that's exactly what we're going to do. If we know or have a hypothesized p value for the proportion in the population, we can use that. Now, if we're doing a confidence interval, we won't know what that proportion is. That's what we're looking for in the confidence interval. So, but we will have a p hat, which is our proportion in our sample, and of course q hat is just 1 minus that, and so we could use this thing right here to approximate that standard deviation, and that's what we'll do when we're building a confidence interval. If we're doing a hypothesis test, of course we can just use this version right here. So of course we can do proportions, probabilities with a binomial, but we can also do approximations with a normal distribution. Okay, so once again, this works pretty well if NP and NQ are both greater than 30, and we can use what's called a z-test and z-interval that approximates the proportion test. And basically, here's how the formula works. For your margin of error, it's just an inverse norm of 1 minus alpha over 2, or inverse norm of 1 plus confidence level divided by 2. And then multiplied by the sigma, but this is the sigma for the distribution of proportions right here. Of course, we're going to suppose we want to solve this for n, which is what this is going to do here. So this version right here is how we would find the margin of error. We would replace this by p hat, that by q hat from our sample. We know our alpha, so we can do 1 plus confidence level divided by 2 for right here. Do an inverse norm. That's from a standard normal, 0, 1. And then we can do this computation and find our margin of error. And then we just take our, it's just the p hat plus or minus that is our interval. Okay, but what if we're solving for the sample size? Well, we can take this formula here, this same formula, and solve it for n. So assuming we know an e, we're going to multiply both sides by the reciprocal of this and then divide both sides by e. That gets us to this point right here, the second line right here in the middle, where we have the square root of n over pq is inverse norm of our 1 minus alpha over 2 over e. Then square both sides, gets rid of the square root, and multiply both sides by pq. So when we get to this point here where we have this green thing here, we have our inverse norm of 1 plus confidence level over 2, 0, 1. That's our standard way of finding the z-score there. We divide by margin of error, we square it, then we multiply by both p and q. Now, if you knew p and q ahead of time, then you wouldn't be doing a confidence interval. So this is a little bit of a question here, but if we have an estimate for this, we could put in p hat and q hat here and use that to approximate our sample size that we need. But the worst case scenario, the thing that's going to make the n the biggest, is if p and q are both 1/2. So what you can do is just, if you don't have a good estimate for about where P and Q are, put in 1/2 here. And so we have, so if we put in 1/2 here and here, that's 1/4. 1/4 is the square root of the square of 1/2. So this 2 here, when you square it, is equivalent to multiplying by this 1/2 and another 1/2. So in the end, we end up with this formula in the box here that's in red that says n is greater than or equal to inverse norm, 1 plus confidence level over 2, 0, 1. So standard and inverse normal from a standard normal distribution. Divide by twice the margin of error, square it, and of course, remember, we always round up. And so this will give us an estimate for how big we need n to be for a confidence interval, given that we have already established a confidence level and a margin of error. Now, remember that this needs both NP and NQ to be at least 30. So if this value is too small, well, if it needs to be at least 30, so really NP times that is half, is going to be half of n, needs to be at least 30. So really we probably should increase to a sample size here of 6 anyway. 60, I meant to say. So if the if this n really is less than 60, you probably should use a sample of size 60 if you're going to be using a z interval. Okay. Continuing on. So this process for computing the 1 proportion z interval is built into the TI-84. So as always, we begin by pressing stat, then left arrow to get to test, choose number A or letter A, 1 proportion z interval, and it will enter the number of successes in a sample. Once again, a success is not something that's necessarily good or bad, it's just the thing that we're counting. Might be a good thing, might be a bad thing, might be a neutral thing. If we are given the proportion of successes in the sample instead, then what we need to do is multiply the sample proportion by the sample size to get x. However, notice that x must be a whole number, so you need to round off if necessary. In fact, it's really not the x that's being rounded off, even though that's kind of really how we do it. Well, the problem is the proportion that they reported has been rounded off. So anyway, bottom line, you got to round off for the x. So here's an example, and it's real easy to use on the calculator. If you can do the stuff we've been doing earlier, this is real easy to do too. Suppose that a random sample of 400 likely voters are polled, and 250 of them support the incumbent candidate for a Senate race. Find a 90% confidence interval for the true proportion of all likely voters who support the incumbent. Notice that the population size is very large, so at least a binomial approximation is going to be good to this hypergeometric distribution of proportions. N, the sample size is 400, that's very large, so NP is going to be about 250, and NQ is about 130 based on the P hat and Q hat. So in both cases, those are well bigger than 30, so a normal distribution approximation is very appropriate. And so we run this 1 proportion z interval on our calculator. We type in the x value, which is 250. The n is 400. The confidence level is 0.9. Hit calculate, and it produces a interval. P hat is our proportion of successes in the sample. That's 250 divided by 400, which is 0.625. 400 is our sample size, and then there's our confidence interval. P hat will be exactly at the midpoint of that interval. And it was uses this formula right here back to where I was. This formula right here for margin of error, and it just does p hat plus e and p hat minus e. We can also use a confidence, that was a confidence interval. We can also perform a hypothesis test, okay, to test for proportions. So again, this is a hypothesis test, and we're used to test the proportion of successes in the sample, p hat, which is x over n, the number of successes divided by the sample size, number of successes in the sample divided by the sample size. And we can test that against some hypothesized proportion, p naught. I'm going to call it p sub 0, to try to not get it confused with the p-value of the test. We approximate the distribution of proportions with the normal distribution, and then find the z-values to standardize to a standard normal distribution. We then use the z-distribution, standard normal distribution that is, to estimate the needed probabilities and inverse probabilities. So basically we just produce this test statistic, which is p hat minus p naught over the standard deviations of the p hats, like a z-score, right? So remember the mean, this is the mean of our sample of proportions is p hat. The hypothesized mean is p naught, and then this is the standard deviation right here, which we're going to approximate by, well, we have an hypothesized p naught this time. So this will be p naught times q naught, or just p times q, or p times q is, remember, it's 1 minus p. Divide that by n there and square root. So that whole thing is the standard deviation that we put there. But in any event, here's a formula for our test statistic, which is a z-score from a normal distribution, a standard normal. Or at least it's approximated well by that if NP and NQ are big enough. And so our null hypothesis is that the true proportion is P naught, that the P hat is, we're given, that's our statistic that we find, our proportion of successes in a sample. We produce this test statistic, Z star, which is P hat minus P naught divided by square root of P naught Q naught over N. And then we can produce P values and critical values. So if it's left-tailed, the alternative hypothesis is that the true proportion is less than the hypothesized P naught. The rejection region then goes up to an inverse norm of alpha, just like it would for a z-test. And then the p-value is done just like for a z-test. It's a normal CDF from minus infinity to z star. And all of these are from a standard normal distribution. So I just put in the 0, 1s there to remember that that's a normal distribution, a standard normal distribution with mean 0, standard deviation 1. And of course, where I have infinity, we know that with a standard normal distribution we can use 10, and negative infinity you can use negative 10 when we put this in our calculator, and the approximations work out just fine. So anyway, if it's left-tailed, we're doing a critical value of inverse norm of alpha, and to the left of that's the critical region. And to find the p-value, we take our test statistic and we find the probability to the left of that, which should be normal CDF. Well, we can just type in negative 10 to z star, 0, 1. For right-tailed, where the alternative hypothesis is that the true proportion is greater than the hypothesized p naught, that's just an inverse norm of 1 minus alpha for our critical value, and then go from there to the right. All right, there, that's typed in correctly now. The normal CDF from Z star to the right forever. So Z star, whatever you figure that out, up to 10, 0, 1 on the calculator would do it. And then the two-tailed test here is from P is just different than P naught. We have for our critical value, we do inverse norm of alpha over 2 and go to the left of that for one critical region, and then go from inverse norm of 1 minus alpha over 2 to the right is the other critical region. So those are the two critical values. They're just exactly the same as they are in a z-test. So a regular z test, this part in the middle is the same, and this part over here is the same, the way you figure Z star is different. That's all. So if P hat is less than P naught, you find the probability to the left of that and double it for your P value. If P hat is greater than P naught, you find the probability to the right of that and double it for your P value. Suppose that a toothbrush manufacturer claims that 7 out of 10 dentists prefer their toothbrush A over a competing brand. We want to test this claim. We take a random sample of 50 dentists and ask which of the two toothbrushes they prefer. We find that 30 of these dentists prefer toothbrush A. Is there sufficient evidence to suggest that the manufacturer's claim is inflated? So let's say we got 30 out of 50, which is 60%. That's a little bit less than 7 out of 10, which would be 70%. But is it enough to call them out on it and say that they've inflated their claim? So we're going to use an alpha equals 0.1 level for this. So note that we are testing the proportion of a sample against a known hypothesized proportion. It's a one proportion test. Since the population size is very large, then we could use a binomial, which we probably should. But since n is greater than 30, and NP and NQ are both, well, they're not that small. Some texts would say a normal approximation will work pretty well. I would say this is probably not good enough. We can test it to see. But let's go ahead and do it with the way the calculator would do it. And the calculator is going to be using these methods here. So you just use, go to Stat, and then right left arrow to Test. It's a one proportion Z test, so we choose number 5. P naught is 0.7, X is 30, N is 50, and the proportion less than that, less than is what we're going to use here because it's a left-tailed test. That's the alternative hypothesis. Hit Calculate, tells us again that proportion less than 0.7 is the alternative hypothesis. There's our Z star test statistic, negative 1.54. Our P value is 0.06. P is 0.6. 60% of the sample was a success, and a sample size of 50. Main thing, of course, you want to pull from that is the P value and compare it to alpha. Since alpha was 0.1, P is less than that, so there is sufficient evidence to say that that works. Now, the correct value really should come from a binomial distribution here. And so if we do it that way, instead of doing it with this, the correct value would be to do it this way over here. The number of trials is 50, the p-value is 0.7, the x value is 30, and just do that probability. That's the probability that we will get more than 30 or less than 30 or less successes in a sample this size if the true proportion was 70%. And that's the real p-value is 0.085. So 0.085 is still less than 0.1, so there's no difference in conclusion at this alpha level, although the p-value is a bit different between 0.06 and 0.085. So if your alpha level was something between those two numbers, then we would reach a different conclusion. With an alpha is 0.1, we would get the same conclusion. There is enough to reject the null hypothesis. We might try a confidence interval. So this is again the formula for the confidence interval. It's p hat minus this inverse norm to p hat plus this inverse norm. And let me rewrite that a different way. So once again, this is just an inverse norm of 1 plus confidence level over 2, 0, 1 times the square root of p hat times q hat over n is our estimate for the margin of error. And so our confidence interval then is just p hat minus e to p hat plus e, which you can see written out here. And these are the formulas that they're using in the built-in program in the calculator. So if we use that method to construct a 90% confidence interval, we can do that with the calculator. Do a 1 proportion z interval, go to stat, test, go down here to A. The number of successes is 30, the sample size is 50, confidence level is 0.9, calculate, and it calculates a 90% confidence interval for the true proportion. So it's saying that we're 90% confident that the true mean is going to be somewhere in this interval, say between 48.6% and 71.4%.